I'm going to record chapter 4 in parts, and so the first part will be over the nomenclature of cycloalkanes and a little bit about some of their properties. Before I start on cycloalkanes specifically, I want to review the concept of isomers. We've talked already about constitutional isomers, or sometimes they're called structural isomers, and these are molecules that have the same formula, but they have different ways that the atoms are connected together. And the conformers could be considered a type of isomer, but all they really are is just bond rotations, and so you're looking at the molecules differently depending on how the bonds have been rotated. You haven't actually broken any bonds to get from one conformer to another. So we're interested in this chapter in the introduction of another type of isomer, generally falling into the category of stereoisomers. And these molecules also have the same formula, but the atoms are connected to each other, to the same atoms, but they differ only in the three-dimensional view. And as a subset of stereoisomers, we're going to be looking in this chapter specifically at geometric isomers. And these will differ only across a plane. And so we're going to talk about cis-trans isomers and what that means. And you could have this type of isomer either on rings or on double bonds. So the first question is, what creates a plane in the molecule? And I've already given you a hint about that, either a ring or a double bond. And why can't they rotate to get to the other isomer? In other words, why are they fixed? Why is this a type of isomer? And so if we have a ring of atoms, those carbons or whatever atoms are all bonded to each other in such a way is that it restricts some of the freedom of motion. And so you have a layer or a plane of atoms, and I've put plane in quotation marks because it's not necessarily a flat structure. And another way you could get a plane, quote unquote, of atoms is if you have a pi bond. And the reason that is that in order for the pi bond to exist, you have to have side-to-side overlap of two p orbitals. And so maintaining that overlap restricts bond rotation. So pi bonds can't rotate the same way that sigma bonds can rotate. And thusly you have the opportunity for sides of the double bond, and so that's another case for geometric isomers. So in this chapter we're going to concentrate on cycloalkanes, and that's the kind of geometric isomer we're going to look at, and then later we'll look at the double bonds and those kinds of geometric isomers. So this ring idea, you could have a top and a bottom, or a left and a right, or however you want to hold it up and look at it. There are two sides to the ring. And you could have all of your groups attached to the ring on the same side, but you can only have two things on opposite sides. And if you have a drawing or a molecule that shows this kind of geometry, then we need a nomenclature argument to add to the name of it so that people will know which one you mean. And in the case where you have a variety of things on random sides of the ring, because we can only have two things for trans or opposite sides, we're going to have some names that we actually can't do until the next chapter. Now let's go back to the rules about IUPAC, or systematic nomenclature. Remember that in that style of nomenclature we have to number the atoms of the parent, and we had to find the parent. In this case, if we assume that the ring is going to be the parent, then we have to number the atoms in the ring. And we want the numbers to still come out as small as possible. So if you have things attached to your ring, one of those is going to be attached to carbon number 1. And then however else you go around the ring, it doesn't matter whether you go to the left or the right or clockwise or counterclockwise, however you want to think about it. You're going to try to go in such a way as to give the things that are hanging off the ring as small numbers as you can. Occasionally you're going to run into a situation where it doesn't matter whether you go left or right from wherever you start, you're going to have a tie, in which case your fallback position is to go in alphabetical order. And what I mean by that is if there's a tie in the numbering system, the first thing that you would write down alphabetically, you'll give that one the smaller number. And we'll look at examples of that. And we're also going to practice using some common names. The IUPAC allowed common names, which we've reviewed already. And we'll also look at a situation where it is possible that a cycloalkane might not be the parent, in which case these things need a group name, which is going to be ending in YL. So we'll see an example of that. So here's an example of a cycloalkane that has a tie. So first we want to know what is the parent. And so when you look at that, count the carbons, you get that there are 5 carbons. And so that would have been, the word for that would have been pentane, but because it's a ring, we put the prefix cyclo in front of it and call it a cyclopentane. And then we want to decide how to number it. So if we start on either the carbon that's attached to the chlorine or the carbon that's attached to the methyl and go toward the other, we're going to get that these two things are on carbons number 1 and 3 of the ring. And so in order to decide where to start, because we have a tie, then we're going to have to start with the thing that comes first alphabetically. And so here's our two choices, and you see the chlorine in the red numbering system is going to come first alphabetically. We'll use the red numbers because it will be carbon number 1 in that case. So in this structure, then the other question is there any geometry indicated? And the answer is no. We can't tell from this picture. This is strictly a two-dimensional drawing. So that means that in the name, we don't have to include any geometrical information. So what is the best IUPAC name? It's going to be 1-chloro-3-methyl cyclopentane. Alright, this molecule is another example, and again we're going to start with finding out what is the parent. So you count the carbons in the ring because that's the bulk of the molecule, or the largest portion of the molecule, and find out what that is. And then you're going to stick the prefix cyclo in front of that. And so when you count, you get that there are 7. So that's a cycloheptane ring. Now we decide where we're going to start numbering. Again, we want to start with one of these carbons that has something on it. And if you start here and go this way, you'll get a smaller set of numbers than if you started over here, or even if you started here and went around. Okay, so let's draw in those numbers. And so now we know what the numbers are, so now we need to know how we're going to write things down. And so we have to decide what groups we have. Well, we have those 2 methyl groups, and then we have this other group over here, which is a 4-carbon group. Now you notice that the 4 carbons are in line, in a straight line, quote-unquote straight line, or normal to each other, but they're attached to one of the interior carbons to the parent ring. So what is the group name for that? The common group name for that. You should also be able to name it with IUPAC, but let's start with the common name. And also, do we have any geometry in this picture? And the answer is no, this is also a two-dimensional picture. Okay, we can't tell from this kind of drawing. So, what is the best IUPAC name? Okay, I said we were going to use the common one first, but I forgot. We're going to have to use a set of numbers for the side chain if we want to use IUPAC. And so there's the little red numbers to show you that it's a separate set of numbers from the parent. So the side chain is a 1-methyl propyl group because this methyl right here is attached to carbon number 1 of the side chain, numbered coming from the parent. The longest that you can go is 3 in a row. So this is a 1-methyl propyl group. And then the methyls are on carbons number 1 and 2. So 1,2-dimethyl, 4 in parentheses, 1-methyl propyl cycloheptane. And what was the group name for that? If you used the common group name, it would have been a sec-butyl. And I put it here ignoring the sec because it's a non-standard prefix. I put it first as if it were being alphabetized by being under the B's. And like I said, it's not real critical about that order because it depends on who's doing it, but we just want to make sure that everybody draws the right picture, and you'd get the right picture from this name. So what does a picture look like that does have the geometric information? Well, we've already seen some ways to indicate the 3D nature around a carbon using the solid filled-in triangles and the dashed lines to indicate that something is coming up out of the plane or toward you, and the dashed one's going back behind or down. So this structure here on the left shows you that these two ethyl groups are coming up off the plane or coming toward you. Or here's another way of doing it. This is kind of an edgeways view, and this kind of view is favored by biochemists in particular. And so you kind of get that idea that these two guys are on the same side and they just didn't bother to draw in the hydrogens. Either one, you know that these two groups are on the same side of this ring. And here's the drawing that would not show you any of that kind of information. This is strictly a two-dimensional drawing. These are both ways of drawing it in 3D. So hopefully you get the idea that if you have shown some 3D information, now is when we have to add that kind of information to the structure. And we know that we have to number such that we give the substituents as small numbers as we can. So we're going to start on one or the other of these two carbons. It doesn't matter. We're going to go from one toward the other to give as small numbers as we can. So I've put in some numbers here. And so we're going to go around the ring. So we have 1 and 3. These two groups are ethyls. And so we'll call that 1,3-diethyl. And then we need to know what it is so that we include the geometric isomer information. And since both of these groups are on the same side, we're going to use the prefix cis, which means on the same side. And so the whole name for this molecule is cis 1,3-diethyl cyclohexane. It was a 6-membered ring. Here's another example. Similarly, if I want to show that I have two things on the ring, they're on opposite sides, one of them will be shown with the broad, bold filled-in triangle up, and this one, the other group, is down, and the hydrogens are both drawn in. Or here's the edgeways view, but again, you still get that idea that this one is up and this one is down. So both of those give you the 3D information. But you have to be really careful if you want to use this kind to draw it in such a way that it looks edgeways. And here's the flat drawing. You see there's no geometric information there. You can't tell which one you're meaning, whether these two guys are on the same side or not. So where are we going to start numbering? Well, by now you should probably get the idea. One or the other of these guys. We're going to have a 1-2 pattern, so then we decide which one is going to be first based on our decision on how to name it alphabetically. So we need to know the group names. So we have a methyl group here, and what is the common name for this group? So we need to include the geometric information in the name, and we need a word to tell people these two things are on opposite sides. And the name for that is trans, and it means opposite sides, kind of like transportation means to carry things across the country or across from each other. So the full name of this molecule is trans 1. I put this one alphabetically according to the iso, propyl, and then 2-methyl, and it was a 4-carbon ring, so cyclobutane. That's fine. Alright, so here's a situation where I have shown the geometry. All these groups are attached to this ring with these bold filled in triangles, which means that they're all on the same side of this ring. And so now we just want to decide how we're going to number it. And you'll notice that it's an 8-sided ring. And so we're going to have to start numbering somewhere on one of these carbons. Remember, you want your total numbers to be as small as you can. So probably starting with one or the other of these guys and going around the ring either clockwise or counterclockwise will get you as small numbers as you can. Now if you fiddle with that for a while, you'll probably realize this way of doing it is the best, because we are also using the group names to help decide that. And so we need to know what those are. So we have a bromo and an ethyl and a methyl, and what is the group name for this? It's a 4-carbon group, but look how they are with respect to each other, and also how that's attached to the parent. If you want to use IUPAC, you can give it a little side numbering system. Again, it's 3 from the point of attachment to the parent is the longest chain you can get, and then I have a methyl off of carbon number 2. So I can use the common name for that is isobutyl, and so I would put all cis out in front of the word so that I know that all these things are on the same side, putting them in alphabetical order. Again, ignoring the non-standard prefix this time. I'm going to put 4 bromo, 1 isobutyl, 7 ethyl, 2 methyl, cyclooctane. Remember, it was an 8-membered ring. Or I can use the 2-methyl propyl group name for this. Here's another example where I have multiple things attached to the same ring and they're not all on the same side. I can only use trans for just 2 things. So I can't say if it's cis or trans because it wouldn't be absolutely clear. Remember, we want to make sure that people are going to draw the right structure. And you could think, well, I'll just say trans because I really mean the methyls, but how would people know that? They really wouldn't know that. So you can't really deal with that geometry problem with this limited set of choices, cis or trans. So all you could do is say that this is 1,2-dimethyl 4-ethyl cyclopentane, and you know that you hadn't given people all the information that they were supposed to have, because we can't use trans. Now, I said that sometimes the ring is not really the biggest part or the parent of the molecule, and so we need a way to deal with that. So let's see an example. If you look at this, there's 1, 2, 3, 4, 5, 6, 7 carbons out here, and only a 4-carbon ring. So probably we wouldn't want to name this as the parent. Another way of thinking about it is if you would have to use parentheses to name this molecule because you were insisting upon this being the parent, that would be more complicated than naming this as a group off of the larger parent, because then you wouldn't have to use parentheses. And I've said before, if you can simplify the group names, then you should do that. So the part that contains the most carbon then is going to be the parent. And So we'll number the chain accordingly. And so which end do you start numbering from? Well, you want to make the numbers as small as possible. So we'll start numbering from the right hand end, and we'll get to a substitution at carbon number 2 sooner than if we had numbered from the other end. And the group name that we're going to use for this, it was a cyclobutane ring, now it's become a group, so we just changed the ending to YL. And so it's going to come in the alphabet under the C's, but CY is going to come after CL. So we're going to put them in alphabetical order, and so you have 2-chloro-5-cyclobutyl heptane. I'm going to stop this recording now.